In the last video of this series, we saw how to derive the Schrodinger equation from scratch for both atoms and solar systems, and discovered that the Schrodinger equation for solar systems or celestial bodies is exactly the same as that for atomic particles. The major difference was replacing the Planck's constant h with the equivalent Planck's constant g that I call the cosmic Planck's constant. Today, we shall be looking at how to solve this equation and try to make sense of the results. This video is a continuation of the other videos of this playlist, Quantum Gravity, and watching the videos before this one is crucial for understanding what is going on here. Otherwise, you will be confronted with some strange concepts that you may even find irritating, for the sheer reason of not understanding the foundation of it all. For those of you who are new here, let me just do a quick recap on the other videos, just so that you don't get completely lost or agitated. To ensure you don't remain lost in the future, click subscribe. In the first video, titled Planck's Constant of the Cosmos, we use circular motion to show that the angular momentum of an electron in an orbit of an atom can be written as follows, from which we extracted the Planck's constant like so. We noticed that the Planck's constant can be written as a function of four fundamental constants, which are the Coulomb's constant, the mass and charge of an electron, and the Bohr radius. You can sub in the values of these constants yourself to confirm that this combination will give you Planck's constant. Hence, we get the Bohr equation as this. This shows that by assuming a planetary model of atoms, we can produce the Bohr model, indicating that the planetary model of the atom is correct if the Bohr model is correct. This model shows us that Bohr missed including the atomic number in his formula, which was the sole reason why his model did not work for bigger elements. If you write the angular momentum as I have, you can analyze any atom. We used the same planetary model approach to derive the angular momentum for planets, but this time the centripetal force was provided by the gravitational force of attraction. We arrived at the same kind of equation from which we extracted the cosmic Planck's constant as we did for the atom, like so. This was where the idea of the equivalence of G and H came from. In the subsequent video, titled Quantization of Angular Momentum in Solar Systems, we got the value of the cosmic Planck's constant as 1.72 exponential 42 joules/second, and used it to calculate the angular momentum of the planets of our solar system, and compared the results with acceptable astronomical data and saw that the results agreed perfectly, indicating that the model is correct. We later showed in the next video titled What if solar systems have electronic configurations, how to use this model to define and write out the electronic configurations for all atoms and solar systems without the need for any of the four quantum numbers you know, which are the principal, azimuthal, magnetic, and spin quantum numbers. We only needed one, which I call the orbital quantum number. Next, we derived the energy equation for both atoms and solar systems in the video titled What if energy is quantized in solar systems, as follows, in contrast to the quantization formula you know for atoms, which is this, and by extrapolation, this for solar systems. We demonstrated that writing the energy in this way accounts very clearly for the fine structure splitting of energy levels and the Zeeman effect. This was emphasized more clearly in the next video titled, "What if the structure of atoms is like solar systems?" All this set the foundation for us to build the Schrodinger equation. In the next video titled Schrodinger equation for planets basics, we used what we had learned to derive the de Broglie equation for both atomic and cosmic particles, and also the Planck-Einstein quantization equations, which we used in the following video titled Schrodinger equation for planets derivation to derive the Schrodinger equation for both cosmic and atomic particles. All the way to this point, we realized that all the equations were exactly the same, the only difference being interchanging G with H whenever we had to move from one of the systems to the other. That cannot be a coincidence. This tells us that atoms are structured like mini solar systems. You can find more proof to verify this fact on my other playlist titled Waves and Particles, where I approach this from the wave perspective and mathematically arrived at the same conclusion. I was able to derive the Planck-Einstein quantization equation again and showed that all waves obey this equation, including light, which showed that light has a medium of propagation which was empty space, and from that, the density of empty space was calculated and dark matter was explained. I will also prove the equivalence of atoms and solar systems from a different angle, general relativity, which will constitute a different playlist. By now, you have seen how I have destroyed quantum mechanics entirely. If you are thinking that there are still some things from special and general relativity that you can use to argue any of my points, I would like to inform you that relativity is also wrong, and I will destroy it too in the same way that I have done quantum mechanics. To ensure you don't miss out on any of this, seeing how 100 years of physics principles go down the drain, click on that subscribe button below this video, and to show your support, click on the like button and share the video. It is time to restore real science and take down this fiction called modern physics. Let us dive into the matter of today's video, solving the Schrodinger equation. The Schrodinger equation for atomic particles is given as follows, and for cosmic particles as follows. The only difference between these two equations is the change of H and G. So, whatever solution I get for any of the equations will be the same for the other. This form of the equation is called the time-dependent Schrodinger equation because it is a function of both space and time. This equation is characterized by the wave function psi, which is a function of space and time. To solve the Schrodinger equation, we need to separate the equation into two different parts, one being a function of space and the other being entirely a function of time. This can be achieved by writing the wave function as a product of two linearly independent functions, phi of t and rho of x. Subbing this into the Schrodinger equation yields this. On the right hand side, we can factor out phi of t so that the equation can be written as follows. Now, let's get all the terms containing t on one side and all the terms containing x on the other, like so. We see that the left hand side is entirely dependent on time, while the right hand side is entirely dependent on space. These two expressions can only be the same if they are both equal to a constant. Let's call that constant c. So, the left hand side is equal to this, and is called the time-dependent Schrodinger equation. And the right-hand side is equal to this, called the time-independent Schrodinger equation. Cross-multiplying leaves the equation in the following forms. In order to know the form of the wave function psi, we first need to know the forms of phi and rho. Let's start with the time-dependent Schrodinger equation. Dividing both sides of the equation by h bar yields this. We see a function phi of t whose derivative is a constant times the same function. This function must therefore be an exponential function. Let's take phi of t to be equal to e to the beta t to be a solution to this time-dependent Schrodinger equation. Then d phi dt is equal to beta times phi. Subbing this into the Schrodinger equation yields this. This equation is true only if beta is equal to c over I h bar. If we multiply and divide the right-hand side by I, we get beta equal to minus ic over h bar. Subbing this into the function phi of t yields phi of t equal to e to the minus ic on h bar times t. Phi of t can be written in terms of sine and cosine as follows. For c on h bar times t to have units of radians, then c over h bar must have units of angular velocity omega. So we have omega equal to c on h bar. Therefore, c is equal to h bar omega. This is the expression for energy. So we have phi of t equal to minus I et over h bar. We now know that the common constant is equal to the energy of the particle E. So the time-independent Schrodinger equation becomes this. To solve this equation for rho of x, one must specify the potential energy function for the given situation. The most famous and simple example usually is the particle in the box problem, where a particle is placed inside a box whose walls are rigid such that the potential outside the box is infinite, while the potential inside the box is zero. According to Born's probability theory, the square of the wave function psi represents the probability of finding the particle in a particular region of space in a given time. Since in this situation we are certain that the particle is inside the box and not outside, then the probability of finding the particle inside the box must be equal to 1, while the probability of finding the particle outside the box is 0. So the wave function is outside the box. Since we already know that phi of t is not 0, and psi is a multiple of phi and rho, then rho of x must be equal to 0 outside the box. So we will have a trivial solution for the time-independent Schrodinger equation outside the box, which is useless. Inside the box, where u is equal to 0, the equation is as follows. Let's bring all the constants to one side to have this. Now, let's equate all the constants to a constant, say alpha, as follows. So the equation becomes the second derivative of rho equal to minus alpha rho. You may not recognize alpha at this point, but let me express it in a way that you would. We know that linear momentum is equal to h bar k. So k is equal to p on h bar. Squaring both sides yields this. Now, let's multiply and divide the right-hand side by 2h to have this. Notice that p squared on 2m is equal to the kinetic energy. So, k squared is equal to 2me over h bar squared, which is equal to alpha. So, alpha is equal to k squared. The general solution of this equation is of the form a sine kx plus b cosine of kx, where a and b are constants. Differentiating these twice yields this. We can factor out minus k squared, and what is left is the function rho that we started with. So we see that the second derivative of rho is equal to minus k squared rho. This confirms that our proposed form for rho is indeed a solution. We require the wave function to be continuous so that, since it is 0 outside the box, it is also 0 at the boundaries of the box. That is, just before you get in. So, rho of 0 is equal to rho of a, which is equal to 0. So, rho of 0 is equal to 0 plus b, which is equal to 0. Thus, b is equal to 0. The equation thus simplifies to this, with only the sign term. Rho of a is equal to a sin ka, which must be equal to 0. A cannot be 0, otherwise, we get a trivial solution that we do us no good. So, the only way for this equation to be correct is if sine of ka is equal to 0. The general solution to this problem is ka equal to n pi. Therefore, k is equal to n pi on a, where n is an integer. Remember that we have already seen that k squared is equal to this. So, subbing in this new expression for k yields this. Making E the subject of the formula, we have the energy of the electron equal to n squared pi squared h bar squared over 2ma squared. Notice that the energy of our electron has become quantized and indefinite. A single electron can now have many different energies, depending on the value of n. This E subscript n is referred to as the energy level of the electron or atom. We now have the function rho of x to an overall constant a. So the wave function psi becomes this. Notice that all the electrons in the atom, no matter their energy level, will have the exact same equation for energy En, since for every electron, n takes the same infinitely many values or numbers. Thus, a single electron can be viewed as being able to occupy all energy levels at the same time, as the equation defining its energy can take infinitely many values. This is where the famous idea that an electron can be everywhere at the same time came from. Now, remember also that this is the same solution we will arrive at if we use the Schrodinger equation for cosmic particles. The difference being that h will be replaced by g. So, the energy equation will be as follows. This therefore tells us that planets can occupy all levels of the solar system at the same time. This is nothing but nonsense. We are quick to believe that that is the case with atoms because we cannot see atoms. But looking at what I have shown you, you see that it is just preposterous. Quantum physicists pride themselves on the fact that the mathematics is correct. You should shut up and calculate. Following from the same mathematics, I have derived the same equations for planets. So what do we do then? If you can prove that any of the derivations I have done is wrong, I will gladly give up challenging this quantum mechanics. Otherwise, you have to admit that quantum mechanics does not describe reality. The reason why the mathematics, though very correct, produces such useless results is that the wave function was taken as a complex numbers that do not exist in reality and hold no physical meaning. Therefore, it also produces a result that does not exist in reality. That is not surprising to me at all. By simply taking away the I from the wave function, all this ridiculousness falls away, while still maintaining all the forms of the equations of quantum mechanics, such as quantum mechanical operators and so on, which allows you to be able to still derive all the quantum mechanical equations, such as the Dirac equation, but this time, equations that will not produce results that violate common sense. Click on that subscribe button and follow me on this journey to rewrite quantum mechanics. Don't forget to like the video if you enjoyed it. And if you feel that this is not correct, please tell me in the comment section why you think so. See you next time.